So, let us look at DC link control. So, we will assume normal operation first of all, normal operation is assumed. So, normal operation means each 6 pulse converter is operating in which mode? 2 and 3 valve conduction mode. That means each 6 pulse converter is operating in 2 and 3 valve conduction mode. And when it comes to one of the sides, that is the inverter side. So, for when it comes to inverter, what is the value of alpha when I say normal operation? It should be greater than 120. Okay. In fact, it is far away from 120, it is much greater than 120. Okay. Now, I will use some notation NB. NB is number of bridges connected in series on the DC side. What I mean, or in other words, a bridge is actually a synonym for 6 pulse converter. Bridge means 6 pulse converter. So, it is the number of bridges on the in the rectifier or inverter, in the rectifier or inverter. Okay. So, the number of bridges should be same because rectifier and inverter are identical circuits. Okay. Now, what we will try to do is try to get a control strategy which is applicable for any of these links. Now, for normal operation we got some equations. See, if you look at the expression for Vd for a 6 pulse converter, we showed that this is equal to VDO cos alpha minus RCID. So, let us assume that the DC side is represented by a constant current and the AC side is represented by a balanced 3 phase voltage in series with an inductance in each phase. So, then Vd, Id, RC, VDO alpha related by this equation. So, we know what is RC. What is RC? It is 3 times x by pi. Is that okay? You recall this? Just go to the 6 pulse converter and normal operation. We got this equation where RC is 3x by pi. X is the inductive reactance of the inductance on the AC side. Okay. Now, what is VDO? VDO, we got the expression for VDO in terms of the line to line voltage of the source. In fact, say the AC side is represented by a voltage source in series with an inductance. So, in terms of the magnitude of the voltage of the source, we can write VDO. So, it is 3 root 2 by pi into V. V is the line to line RMS value of that source voltage, 3 phase source voltage. Now, if I multiply this equation, by NB. Now, if I multiply this by NB, this equation, I get NB into VD on the left hand side, NB into VDO cos alpha minus NB RCID. Now, if you look at go back to any of these links, suppose I go back to say the most common one, bipolar link. Okay. Now, in the circuit, I have an AC bus on the rectifier side. See, this is this AC, this is the AC bus. This is one of the buses of the AC system. There is another AC bus on the other side. This is the AC system bus. See, one point to note is that this DC link is present in predominantly AC system. Okay. So, the two buses on the extreme left and extreme right are AC system buses. Now, what we do as on the AC side, see, we need a model. So, what is the model that we are using? See, to the left of or to the on the AC side of the converter, what is the model used? If you just go back to 6 pulse, what is the model used? AC voltage source in series with an inductance. Now, the AC voltage source is nothing but the bus voltage, and the inductance is nothing but the transformer leakage inductance. Now, we ignore the transformer leakage inductance when we try to do some analysis for 12 pulse LCC. Okay, but that can't be ignored. That that neglecting the leakage inductance was for the sake of simplicity to show that some harmonics get eliminated. Okay, so leakage inductance is actually something which is non-zero, and it can't be neglected. So, the leakage inductance serves as the inductance that is appearing in the model of the AC system, that is appearing on the AC side of the converter. Okay. So, I have a 3-phase voltage source with an inductance. Now, if you go back to the 12 pulse LCC, I have one YY transformer. There is a leakage inductance and there is a representation of the AC voltage, which is nothing but the AC system bus voltage. Now, when it comes to one more transformer, there is Y delta. Now, what I do here is, I will assume that Y delta transformer can be also represented by the same inductive reactance corresponding to leakage, and another set of voltages. Only thing is, the two voltages are identical except for what? Phase shift, that is all. So, one assumption made here is the leakage inductance, the equivalent leakage inductance for both YY and Y delta transformer are same. That is the assumption. Okay. Now, this assumption is something which is necessary, and it is not very much deviating from reality, in fact. Okay. So, it will help us in trying to do further analysis, and it is not far from reality. Okay. So, the assumption is this V, what I am talking about, see this V in the expression for VDO, there is a V in the expression for VDO. Okay. So, V is RMS value of line to line voltage. So, if I take either the one of the bridges on the rectifier side or inverter side, so V is the RMS value. I take one at a time. Suppose I am considering one of them. So, V is the RMS value of line to line voltage of the AC system bus. Okay. And X is the leakage reactance of the transformer. Now, this is something which is assumed to be same for both YY and Y delta transformer, assumed to be same for both YY and Y delta transformers. Now, if I make this assumption, it means that the equation that I have written here has the same value of RC for all the bridges. Of course, VDO is same. Please note, they are all connected to the same AC system bus. When it comes to RC, which is dependent on leakage reactance, with this assumption, all these have the same value of RC. Now, multiplying by VD, what is the purpose? The left hand side, if VD is multiplied by NB, the number of bridges. Now on the DC side, the connection is in series, So the average voltage that I effectively get on the DC side is sum of the voltages of the individual bridges or 6 pulse LCCs. So NB into VD gives the total average voltage on the DC side. So that is given by NB VDO cos alpha minus NB RCID. So what I am trying to say is this particular equation is this equation. This equation is something which is applicable for all the bridges. So since it is applicable for all the bridges, if I just multiply the equation by NB, I get a resulting equation which is applicable for the rectifier side or inverter side. Okay. But one point to note is that when it comes to consider both, that is both rectifier as well as inverter, then we need to take into account that the AC side system voltages can be different on the rectifier side and inverter side. Okay. So let us see how to analyze this using this. So our equation will be from now on this one, NBVD is equal to NBVDO cos alpha minus NBRCID.
This equation is common for all bridges. Only
This equation. See, this equation 1 is common for all the bridges. From that I get 2.
Yes, but for the equation 1, alpha will keep changing, right, for all the bridges.
See, if you look at the definition of alpha, you can fix alpha as the value for one of the bridges. For the other bridges, it's just delayed. See, if you take 12 pulse, fix alpha for one bridge, say YY, the one connected to YY. For the one connected to Y delta, it is just delayed by 30 degrees.
So, but when I am solving, then I will plug in that delayed value, right, here for the second bridge.
Yeah. Now, when it comes to the second bridge, even the source voltage is also shifted. It's not just the pulses are delayed, the voltages that are applied are also shifted by 30 degrees. So, the equation is still applicable. Yeah, only thing is all the things are happening at a later instant, that's all. So, it's identical operation, but a delayed operation. Okay. Now, when it comes to bipolar, so there are two 12 pulse LCCs. Now, these two 12 pulse LCCs operate identically. That means, if I take the one bridge connected to the YY in the first 12 pulse and another bridge connected to YY in the second 12 pulse, they are identical. Only thing is the one connected to Y delta will be delayed in operation, that's all. Okay. So, when it comes to average, so please note, when it comes to average, it's easy to actually do the analysis, just multiply it, because average, if you have two voltages in series and you know that the first voltage has some average value, second voltage has some average value, the resultant average is sum of the averages. That result we are using, that's all. So, instead of two voltages, I have NB voltages. Okay. Now, if I want to show a very general arrangement which is common to any of the DC links, I use a different figure. So, I just use this general diagram again. Again this is another schematic diagram. Suppose I show the rectifier side. So, please note, now I am slightly changing the meaning of the schematic diagram. This schematic diagram stands for a transformer with a box with a rectifier. A box with a thyristor actually means one side, either rectifier or inverter. It can be having two such things in the case of bipolar, one such thing in the case of monopolar, or two or more in the case of homopolar, whatever it is. So, suppose this side is a rectifier and this is a inverter. Now, I will give some names for the voltage here. Suppose ER is the line to line voltage of the AC system bus on the rectifier side, and EI is the RMS value of line to line voltage of the AC system bus on the inverter side. The two need not be identical, they are not same buses. Okay. Then of course, the current here is ID. Suppose I call the voltage between the two conductors. So, in the case of bipolar it is two conductors, in the case of monopolar it is conductor and ground, in the case of homopolar it is any of the conductor and ground. Okay. Suppose this voltage is say Vd, I add one more subscript R to mean that it is rectifier voltage, and suppose the voltage here is Vdi. Okay. So, there is a transformer on the rectifier side. Suppose I take one of the transformers, that is one of the YY transformers. We know that the number of turns on one side is N1 and the other side it is N2. Now, to differentiate between the transformer on the rectifier side and inverter side, I add one subscript R for rectifier. Okay. And in addition to the number of turns which are constants, as I mentioned, for the sake of controlling voltage we have tap. So, I have to include tap. Suppose the tap is on the side which is connected to the AC system bus, there is a tap. Again, T is the notation for tap and R is the tap for rectifier. Okay. So, on the inverter side also, N2I is to N1I and Ti is the tap on the transformer of the inverter. Now, I make some notations. Define EDR as okay. And before defining EDR, let me define one more quantity, EVR. EVR as N2R by N1R TR ER. Now, what is the purpose of this definition? See, if you look at the transformer on the rectifier side, the voltage that you get on the other side of the transformer, if the one side the voltage is ER, the other side is N2R by TR N1R ER. Now, I will not show that as the voltage at this point because the transformer is not an ideal transformer, it is this ideal transformer plus a leakage reactance. Okay. So, I cannot show this voltage EVR in the figure. Please note that, because I have not shown inductance. The leakage inductance also if I had shown, then I could have shown this. Now, the subscript V indicates the valve side voltage. See, one is the AC system side voltage is ER, EVR is the valve side voltage, V for valve. Okay. Then we also define on the inverter side EVI as N2I by N1I TI EI. So, one can, okay, let me write this. ER is RMS value of line to line voltage of AC system bus at the rectifier side. When it comes to EI, it is also the RMS value of line to line voltage of the AC system bus at the inverter side. Now, if I take this voltage on the at the DC side terminal of the rectifier, which is VDR. Now, can I write an expression for VDR in terms of EDR or okay, in terms of EVR, okay, I think let me go back to this, the equation I have. NBVD is NB VDO cos alpha minus NB RCID. Now, what is NBVD? It is the total DC side voltage. Now, so it is nothing but VDR. It is nothing but VDR. Okay. So, in place of VDO, what do I have? What do I have? Say, I take this equation. NBVD is equation number 2. NBVD is equal to NB VDO cos alpha. First term. Let me take one term at a time. NBVD is VDR, that I have already written. Okay. Now, if I take the right hand side, first term is NB VDO cos alpha. Of course, let me write cos alpha first. That is one of the factors in the first term. Now, again to differentiate between the alpha of the rectifier and inverter, I add a subscript R, alpha R. Now, the remaining factors, NB VDO. What is NB VDO? Using the notations.
Root 3 times ER.
Sorry?
Root 3 ER.
Root 3? Is it just
V we will use root 3 ER. V we will do
ER or EVR? EVR. See, that transformation, you have to take the transformation also into account. See, if you look at the AC side representation, when we did earlier, what we get as a voltage source on the AC side is the transformed voltage. So, the transformation also has to be taken into account. So, it is the transformed voltage is not ER, it is EVR.
But we take voltage which is behind the inductance, right?
Yeah, that's EVR.
EVR is after the inductance.
Okay. See, okay, if I have, suppose I have a transformer. Okay, suppose this is N2 by N1 or whatever, okay, N1 by N2. So, this is the representation. Suppose this is V1. Okay. Now, this representation, when you look from this side, is a voltage source in series with a reactance like this, which is N2 by N1 V1 and a reactance. See, we are looking at the transformer from this side, So, when you see from the converter side, it is the transformed voltage that you see. Please note, we are trying to see from the converter side. So, what we need to do is write it in terms of EVR, not ER. Okay. What is the expression? In terms of 3 root 2 by pi into root 3. Why root 3?
Because line to line.
No. All these are line to line voltages only.
Oh, these are line and
EVR into NB. Okay. So, that is the first term on the right hand side. Now, what is there on the right hand side as a second term? Minus NB RCID. If you look at equation 2, there is NB RCID. So, I will write this as minus RCR ID, where I have just introduced a notation RCR, which stands for NB into RC. That's it. Instead of writing NBRC, I am writing RCR. Okay. Now, this is as far as the rectifier is concerned. Now, if I want inverter, VDI. So, if you look at this circuit, the inverter side DC voltage is VDI. Now, please note VDI is not equal to VDR, because the transmission line can have a resistance and hence a drop across this resistance. Okay. Okay, now before coming to this special case, I mean, if you go back to the analysis of 6 pulse converter, we had defined one quantity called VDI, if you recall. Just go back to the recall what we did for 6 pulse LC. We defined a quantity called VDI, which is nothing but minus VD. And we also derived a relationship between VD, ID, RC and gamma. So, if you can recall, this is equal to VDO cos gamma minus RCID. You recall? Now, when it comes to inverter, VD is negative, VDI is positive. Now, what I have shown here is not the usual VD. VDI in this figure is not the usual VD, it is negative of VD when it comes to inverter. So, VDI is negative of the usual DC voltage that we considered for the 6 pulse LCC. Now, if I do similar manipulations, again multiply this by NB. So, from this I get NB VDI is equal to NB VDO cos gamma minus RCID into NB. Now, equation 2 and 3 are slightly different. 2 is in terms of alpha, 3 is in terms of gamma. Okay. So, we will see why gamma is used for inverter, alpha is used for rectifier shortly, but before that, can we write from this equation 3, can we come back to this figure and get a similar equation as we did for rectifier? So, what is VDI? Similar to just the previous equation, it is 3 root 2 by pi into sorry. Yeah, okay, go back to this equation, equation number 3, is there any minus there? I want to write it in terms of gamma, okay. So, we will see why we write it in terms of gamma is something which will be obvious shortly. So, if we write it in terms of gamma, it is 3 root 2 by pi E Vi NB cos gamma. Now, again, to differentiate between the gamma of rectifier and gamma of inverter, I use a notation gamma I minus, should I differentiate between, say, RCR is the resistance corresponding to rectifier. Now, I use a notation RCI for inverter, is that okay? Are the two inductances or reactances different? Same. Depends on, transformers are identical, then same, yeah. Now, they are same provided the taps are same. Please note the taps in general are not same. See, the inductance, effective inductance that comes into picture depends on tap. I mean, these are tap changing transformers. The depending on the position of the tap, we have the value of the inductance. Okay, this is something which you would have studied in a power system course or in an advanced power system course, not in an undergraduate course. Okay, so I mean, I will not try to cover that in this course. Okay, so the point to note is the leakage inductance is dependent on tap. That's the point. So here I have written in terms of gamma. Why? What is the significance of gamma for inverter?
Commutation margin angle.
Yeah, see, commutation margin angle is a very important thing when it comes to inverter, and for normal operation, whenever alpha is greater than 120 degrees for inverter, gamma I is commutation margin angle of inverter. For normal operation. So, normal operation means alpha greater than 120 degrees. Now, I will use a few more notations. Define EDR. I have already defined ER, EVR. Now, I am defining EDR as 3 root 2 by pi NB EVR into cos alpha r. And I also define EDI as 3 root 2 by pi NB EVI cos gamma I. So, if I just look at the two equations, let me call this as equation number 4 and equation number 5. So, if you look at equations 4 and 5, 4 can be written as VDR is equal to the first term on the right hand side, just now I have a definition EDR. So, VDR is EDR minus RCRID, and equation 5 becomes, with the new definition that I have for EDI, it is VDI equal to EDI minus RCI ID. Now, it appears as if I can draw some equivalent circuit corresponding to these two equations. So, if I call these equations as 6 and 7. So, if I take equation 6, I can have a circuit equivalent for this equation 6. So, the circuit equivalent is like this: a voltage source in series with a resistance. So, the resistance is RCR, the voltage source is EDR, and the current that is flowing is ID. And what I have as voltage at these two terminals is VDR. Then similarly, on the inverter side, I have an equation, equation 7. I can draw an equivalent circuit for this equation 7. The voltage source is EDI minus RCI, the resistance, and the current is same ID. The voltage at these two terminals is VDI. Now, between these two terminals, or these two ports where the voltage is VDR and VDI, what is there? What is there? So, no, what is there? See, if you go back to the circuit, VDR is the voltage of the DC side. No, it is a transmission line. Okay. So, in general, there can be a link. If there is no transmission line, if it is just a back-to-back converter, say if there is no transmission line, if the converter, both the converters, rectifier and inverter are at the same location, we call it as back-to-back converters. There is no transmission line. Okay. So, whether there is transmission line or not, we can represent the equipment between these two by a resistance. If there is no transmission line, this resistance is 0, that is all. So, I will use a notation for this for this resistance RD. Okay. So, this is the equivalent circuit. So, this is the equivalent circuit corresponding to equation 6 and 7 after taking into account that if there is a transmission line between the rectifier and inverter, it is represented by just a resistance. Okay. So, I will stop here.